Hello, this is our second video on the chi-square distribution. This one will cover goodness of fit test. Here's our introductory example. Let's say you wanted to know if a particular die you have is actually a fair die or not. Maybe you're a Las Vegas casino or something like that, and you want to just test, does this die give us the numbers 1 through 6 and make each of those equally likely? Okay. So how could you answer that question? Well, first you would collect some data, a sample. And let's say we roll the die we have 120 times. I'm just picking 120 to be a nice number divisible by 6. And I use StatCrunch to simulate the die rolls. And then I've got the simulation data in the table here under the observed column. In my simulation, 19 out of 120 of the rolls came out 1, 28 of them came up 2, etc. Okay. Now, if the die were fair, we would expect about 20 out of 120 for each number, 20 for 21s, 22s, all the way up to 26s. You would never get exactly that, but that's the expected value based on each of the numbers being equally likely. Now, in this case, based on what we have in the table, the question is the distribution of observed results, what we have in that column, is that different enough from the expected results that we should conclude that the die is not fair? And the number that has the biggest difference is 2, right? We got 28 rolls to come up 2. We expected 20. That's the biggest difference we have. Some of the others are bigger and smaller, but the question is, are those differences on average enough to conclude the die is not fair? Okay. Now, our hypotheses will be as follows. Again, these are going to be in words, not equations, because you have a whole bunch of different values that you're comparing, not just one. So, the null hypothesis is the observed distribution of die rolls fits or follows the expected distribution. And the alternative hypothesis is just that the observed distribution of die rolls does not fit or follow the expected distribution. The only real difference is does fit versus does not fit. Every time you do a goodness of fit test, your hypotheses will look like this. All right, now let's examine this using statistics, okay? The test statistic, just like with the test for independence, will be called the chi-square statistic, and it's going to have the same formula that we looked at in the last video. You sum up for all the different values of the categorical variable. In this case, we got 6 values, 1 through 6. We take the observed minus the expected, square it, divide that by the expected. Okay. So in this table, I've added the squared differences. That's the numerators of the numbers we're adding up to get the chi-squared statistic. 19 minus 20 squared is 1. 28 minus 20 is 8. Square that, gets 64, etc., all the way down. And so from this, we get chi-squared is equal to, adding up those 6 fractions, 98 over 20, or 4.9. That 4.9, that is the chi-squared statistic for this contingency table. Okay. Now, again, we'll usually use StatCrunch to do this, so you won't have to do this on your own by hand, but you can see it's pretty intuitive how this happens. Big differences between observed and expected are going to give you big values for the chi-squared statistic. All right, so if you want to do this on StatCrunch, how do you do this? Go to Stat, and whereas before for the test for independence we looked at tables, now there's actually a goodness of fit option most of the way down the table, so we pick that, and then we pick a chi-square test. When you hit that, you get this pop-up box, and it's pretty easy to fill in. Your options are observed and expected, and however you have your table labeled, for the observed, you would pick whatever column those frequencies are in, the ones you got from your sample. And for expected, you would pick wherever your set distribution is, the one you're comparing to is. If you want to, you can pick some of the options in display, but those are typically not required. You just want to pick the correct two columns. Great, so let's do that for our data. Okay. All right, here's the results we got. It's labeled chi-square goodness of fit results. We have n equals 120. That's telling us we had 120 total in the sample, or 120 rolls. Degrees of freedom is 5. Notice we have 6 rows and 2 columns. 6 minus 1 is 5. 2 columns minus 1 is 1. 5 times 1 is your degrees of freedom. The chi-square statistic is 4.9, and the p-value that goes with that is, in this case, 0.4282 to about 0.43. So this gives us enough to complete our hypothesis test. Okay. Step 3, we report the chi-squared statistic and p-value. Step 4, we fail to reject the null hypothesis at the alpha equals 0.05 level. The p-value is larger than that alpha. And the conclusion is, we do not have sufficient evidence to conclude that the observed die rolls do not follow the expected distribution. In other words, we cannot conclude that the die is unfair. The differences between the observed and the expected is not large enough to show statistically that this is not a fair die. All right, so that's an example of a chi-square goodness of fit test. Let's do another example. All right, let's talk about an actual study done in China on the COVID virus. Okay, doctors there noticed that certain blood types seem to be more susceptible to becoming ill from the coronavirus than others. And they collected some data from 1,775 COVID patients, those who tested positive. And this table shows the observed percentages and expected percentages. So, of those who had come down with the virus, 37.75% of them were type A, 26.42% of them were type B blood, 10% AB, and 25.8% were type O. All right. Now, compare that with the expected percentages in the larger population in that area. In that area, 32% of individuals had type A blood, about 25% type B, 9% type AB, and almost 34% type O. Okay. Now, if you compare these percentages, you can see type A, the observed percentage is bigger than the expected percentage by over 5%. That could be significant. Type O, 26% of the observed in the observed column and almost 34% in the expected column. That's a pretty big difference. The B and the AB look pretty close to the same. Okay. So the question is, are these differences in percentages statistically significant to show that there is a difference between the people testing positive for COVID and those who are not? Now, the problem is, to do a chi-square test, you need frequencies, not percentages. So if the data is presented in percentages, we need to convert that to frequencies. But that's pretty easy. We just take the sample size, 1,775, multiply that by each of the percentages in the percentage table, and you might have to round off to the nearest integer, but you can do that and create this second table, which shows us the frequencies. Out of the 1,775, 1,670 of them were type A, 469 were type B, etc. Okay, so it's this frequency table that we're going to have to use to conduct our hypothesis test. All right, so let's go ahead and do that. All right, this is the full 5-step process for this chi-square goodness of fit test. Again, our question is whether certain blood types are more susceptible or less susceptible to the COVID virus. Okay. Step 1. Our null hypothesis is the observed distribution of blood types for COVID patients fits the expected distribution of blood types. And we'll go ahead and set a level of significance for this one of 0.01. The alternative hypothesis I don't have written here, but you would basically just change this to a do not. The observed distribution of blood types for COVID patients does not fit the expected distribution of blood types. That'd be your alternative hypothesis. All right, step 2, we're going to use a chi-square distribution with 3 degrees of freedom. We have 4 rows, 2 columns. 4 minus 1 is 3. 2 minus 1 is 1. 3 times 1 is 3 degrees of freedom. All right, then you would go to StatCrunch. You would have to put this table of frequencies in StatCrunch and then select chi-square goodness of fit test. All right, in this case, we get a chi-squared statistic of 54.6 and a p-value of less than 0.0001. And if the graph here that I've got of the chi-square distribution for 3 degrees of freedom, you can blow that up if you want to zoom in on it. 54.6 is way, way, way off on the right, out of the window for this graph. That's a very, very high chi-squared value, and so we're getting a very, very low p-value. So that means step 4, we reject the null hypothesis at the 0.01 level of significance. Okay, so that means our conclusion is we do have sufficient evidence to conclude that the distribution of blood types among COVID patients is different than that for the larger population. Okay? Now, again, our conclusion is basically stated in terms of the null hypothesis. You can certainly observe from the table that it looks like type A, people with type A blood are more susceptible than average to the COVID virus. Type O blood types are less susceptible. Okay, strictly speaking, the chi-square test doesn't tell you that. It just tells you that the distributions are different. But knowing what this test produced, we could now go in and do a proportion test on type A blood and see if people with type A blood are more susceptible than people of type O blood. We could do a 2-sample proportion test if we wanted to do that. All right, so that wraps up this video on goodness of fit tests. In the next video, we're going to look at what are called tests for homogeneity.